want to run you through some of the key models in the timeline of the development of the atomic theory. The very first model that we discussed, and really the very first model of the atom, was Dalton's model. It was called the billiard ball model, and we laughed at it a bit because it's really nothing more than a solid sphere. Had no internal structure, no empty space, no electrons, no protons, no neutrons. If you're unfamiliar with the term billiard ball, it really just means pool ball. And I'm going to attempt to spell billiard now. I'm positive that might be wrong, but his early model of the atom, it wasn't great, but it was a stepping stone for us to move forward and really refine down what we think the subatomic world really looks like. Nagaoka was a Japanese philosopher and scientist, and he had an early planetary model. It was actually really good. His model was widely overlooked, not because of its flaws, but because at the time, unlike now, Japan was not considered at the forefront of science, and the Western scientific community largely ignored his proposed idea, though it had many good characteristics. By planetary model, what we mean is that he placed a positively charged core at the center of his atom, and around the outside, he had electrons, which had been recently discovered by J.J. Thomson, who we'll get to momentarily, circling just like cars in a traffic circle. He was inspired by looking out his window and looking at the roundabout in Tokyo Square. The issue with this is that it's unstable. Positive and negative charges are attracted. So if the electron orbited the core like the planets orbit the sun, it would eventually collapse on itself. So we know this model of the atom can't be right because things exist. If this were the way it really were, then there wouldn't be anything at all. The protons and neutrons would collide, electrons would collide with one another, and we would have no visible matter in the universe. J.J. Thomson used the cathode ray tube. I demonstrated it was that kind of halogen light to discover the electron itself and won the Nobel Prize for it. So he was very popular, very widely respected, but he came up with a horrible model of the atom. But people liked it for a long time because they really liked J.J. Thomson. It was called plum pudding. So J.J. Thomson, not surprisingly, featured his discovered electron very prominently in the plum pudding model. He plunked them down inside what he called a positively charged jelly. So the proton, neutron, and the nucleus itself had yet to be discovered. So no one was quite sure where these particles were. So Thomson assumed that it might just be kind of evenly distributed everywhere, and the electrons were plunked inside. Now the problem with this is the aluminum foil experiment we discussed with Philip Lenard had shown that the atom must be mostly empty space because the electrons pass directly through the foil with almost no resistance. So if this was the way the atom looked, then all the electrons shot at the aluminum foil should have been reflected, but they weren't. So Thomson's model's primary flaw is that it has no empty space. It's better than Nagaoka's in this way in that it's stable, it won't collapse on itself, but it's missing a few key features. Really the final piece before we get to what is really a good model of the atom is Rutherford's model. He also did a fancy foil experiment, but instead of electrons, he shot positively charged alpha particles at a gold foil. And he confirmed that the atom is indeed mostly empty space. Most of the particles just passed right through the foil as if it wasn't even there. But some were deflected at large angles, and some bounced right back at the alpha particle source. This indicated that the atom had a positively charged core, confirming the existence of the proton, and now we knew that it was centered in the atom, and Rutherford called this the nucleus. And around the atom, he placed the electrons much like Nagaoka did. The only difference is it was much more stylized. So I always call this the Jimmy Neutron model of the atom. We still see it today because it's like cool to look at, but to be honest with you, it's really just ripped off Nagaoka's model with the circles turned sideways. So we have the billiard ball, Nagaoka's planetary model, Thomson's plum pudding and the Jimmy Neutron model of Rutherford. It wasn't really called that because like this was 1914 and then Jimmy Neutron was not then, but that's what I call it. So the Bohr model of the atom is what you're studying now. So if you've made it this far, okay, or you skipped over it, part 2 coming up is where we're going to discuss the Bohr model of the atom. All right, guys, we're going to talk about the Bohr model now. So this is kind of the end point in the unit we're on. The Bohr model is not our current model of the atom, but it's pretty good. The current model of the atom is really amazing, much more complex than the Bohr model. It's called the quantum mechanical model, and we'll be talking about that in great detail in Unit 2. But the Bohr model is our endpoint here, and it works well enough that we can use it to discover all sorts of things about chemistry. Bonding, how compounds are formed, how ions are formed, and the best part about Bohr's model, it's easy to draw, it's easy to understand, and it's stable. So let's transition over to the periodic table, and we're going to pick out an element here. Actually, we're going to pick out a couple. So let's take a look at the simplest element, hydrogen. We know that its atomic number is 1. That means it has 1 proton. The proton determines the identity of the element. If an element has 1 proton, it is hydrogen. I'll repeat that because it is of critical importance. The number of protons an element has determines the identity of the element. So hydrogen has 1 proton, and we look, the most common isotope of hydrogen is 1. So we're going to keep that in reference. Let's say we want to use another atom and compare 2 Bohr models side by side. We'll use a common one you've heard of, oxygen. Oxygen has 8 protons, an atomic number of 8, and its most common isotope is 16. So let's see if we can draw the Bohr model of the atom for hydrogen and oxygen next to it. So we'll go back over to this side now. First, the simple hydrogen atom. So if I write my notation for hydrogen this way, I'm using isotope 1 of hydrogen. I don't even need to indicate that there's 1 proton here, because if I say hydrogen, you know automatically this must have 1 proton. The protons equal 1. Now, if the total number of particles in the nucleus is 1, and one of that 1 is a proton, how many neutrons does it have? If you said 0, you're correct. The most common isotope of hydrogen has 0 neutrons. Now, we don't see any charge here, so there's no positive or negative symbol written, so that means that this is hydrogen atom, so it has not gained or lost any electrons. So for it to be neutrally charged, protons are positive, so to balance out that 1 positive charge, there must be 1 electron. So how do we draw the Bohr model? Well, for me, what I do is I'm going to take and simply draw a circle in the middle and say that there's 1 proton here. You could draw all the individual little circles if you want to, protons and neutrons. It's really not necessary, and I'll show you why when we look at oxygen. It begins to get very cumbersome as the nucleus becomes larger and larger. Now, the key feature of Bohr's model are that it has energy levels. So only a certain number of electrons are permitted in any given energy level. In the first energy level, we can fit a total, a max of 2 electrons. We can put in 1 if we want to. We can put 2 if we want to. We can't put any more than that. So it can fit a maximum of 2. If we're drawing hydrogen, we said we only need 1 electron. So I'll place 1 electron here in the first energy level for hydrogen, and that would be an acceptable and appropriate Bohr model for hydrogen. Obviously, you wouldn't need to label the first energy level. I'm doing that for teaching purposes. Let's take a look at oxygen now and see how it differs. Now, do you notice anything bizarre here? I've written oxygen 18. You might be thinking, I thought you said oxygen 16 was the most common isotope. Indeed it is. but other isotopes of oxygen do exist. That's why we see decimals on the periodic table. Those are averages. So I'm telling you specifically that this is isotope 18 of oxygen, but it's still oxygen. So how many protons does oxygen have? Well, if you look at your periodic table, you'll find oxygen must have 8 protons. It can't have any other number of protons because the proton determines the identity of the element. So oxygen has 8 positive charges in its nucleus. Now the question is, this specific isotope of oxygen, oxygen 18, which is pretty far from the average, so it would be a rare isotope of oxygen, probably radioactive. If it's oxygen 18, how many neutrons does it have? Well, this number tells us that the total number of particles in the nucleus is 18. 8 of the 18 must be protons. So that means there are 10 neutrons, neutrally charged massive particles that reside in the core of the atom. Now, notice again, there's no positive or negative charge here, so this is oxygen atom, not ion. Oxygen atom has no positive or negative charge, so to balance out the 8 positives in the core of the atom, that must mean there are 8 electrons. So to draw the Bohr model here, I'll again start with a circle. This time I'll say protons equal 8, neutrons equal 10. I'm not going to draw all the individual circles, though if you're feeling artsy and you want to color code them, that's wonderful. Live your best life. Now I need to put in a total of 8 electrons. Remember, from hydrogen, we can fit a maximum of 2 in the first energy level, so I'll place those here now. For the time being, where you place them makes no difference to me. We'll practice more and more, and you'll start to see a pattern in the way that I place the electrons, and then we'll study it much more in-depthly in our next unit. So the first energy level, I'll label it again for our purposes. So this is the first PEL, or the first principal energy level. It can only fit a max of 2 electrons. It can fit less, but it cannot fit more. I need a total of 8 electrons in oxygen. I've placed 2, so how many more do I need? 6. So we must move up to the second energy level. These electrons are further from the nucleus. They have more energy, as you would expect. We call this the second principal energy level, or PEL. And the number of electrons that can occupy the second principal energy level is 8. So a total of 8 electrons can fit here. We don't have to put 8, we can put fewer, but we can't put more. So oxygen needed a total of 8. We've already placed 2. So now we need to place the remaining 6 for oxygen. So we have 1, 2, 3, 4, 5, 6. So here we have a Bohr model for oxygen. Now you might be thinking, Hef, why didn't you just put all 8 in the second energy level? Why not just skip the first one entirely? Well, much like human beings, electrons are very lazy, and they like to be in the lowest possible energy state that they can be. So these 2 electrons aren't just going to jump up to the second level. That takes effort. They'd much rather reside in this lower energy state. The electrons build up in the atom, kind of like building up in the steps of a skyscraper. This is actually called the Aufbau principle. It's a German word that means to build up. So the atom builds up from the lowest energy out to the highest energy levels. For your sake, in the Bohr model, we're not ever going to use anything beyond the third energy level. And the third energy level, or third PEL, has a special rule to it that I'll explain in class tomorrow. The third principal energy level can fit 18 electrons. Now, there's a catch, though. it can fit a total of 18, but only 8 at first. So if I wanted to continue building up an even larger atom, I would put 8 electrons in this third principal energy level, the third ring of the atom. Once 8 are there, I actually have to jump up to the fourth principal energy level, place 2 here, and then come back down and fill in the remainder. Now, I told you we're not going to go anywhere beyond the third energy level for 2 reasons. One, it gets a little confusing, but I'm not omitting it because it's confusing. This is honors chemistry. I'm omitting it because this exposes a flaw in the Bohr model. We had talked already that it's not the current one, so there are issues with it. Now, I want to show you one trick on the periodic table, though. So follow me back over here, and this will be the last part of the video. If I read the periodic table like a book, so from left to right, do you remember how many electrons fit in the first energy level? 2, right? If I trace across, how many elements are in the first line of the periodic table? 1, 2. Now, in the second energy level, we said we could fit a total of 8 electrons. Well, how many elements are in the second line of the periodic table? 1, 2, 3, 4, 5, 6, 7, 8. Now, in the third energy level, I said we can fit 18, but there's this special rule, right? Notice, you see there's a gap here in the periodic table. That lets you know something's up. And I said, you have to put in 8 first. The third line of the periodic table actually goes like this. And we put in 1, 2, 3, 4, 5, 6, 7, 8. And then I said this weird thing about, oh, you got to jump up to the fourth and put 2 in. Well, the periodic table tells us that too. So when I put in 1, 2, 3, 4, 5, 6, 7, 8 in the third energy level, guess what? I'm in the fourth energy level here at potassium, and how many elements are there if I'm reading across? 1, 2. Now I'm back in the third energy level. It goes like this. And I said we could fit a total of 18, so that means in this section there are, you guessed it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a ton of information locked up in the periodic table that we're going to unlock together. If you were confused by any of this, I'm not surprised. The main objective for you in this video is if you can construct a Bohr model and remember this simple fact, 2, 8, 18. That's how many electrons can go in those energy levels. 2, 8, 18. And if you can fill those dots in and figure out protons, neutrons, and electrons, you have learned enough to have a high degree of success on the upcoming assessment. So I'll see you in class. I hope you enjoyed the video.